So one thing I want to point out before we do the last distribution is that we were talking about LeBron James. It's theoretically possible that the first make never happens, or that he needs to take 1,000 shots before he makes it. So the point is, if you kept using this formula, let's suppose we want to know what's the chance he gets it on the 15th. You can see it's incredibly small that it takes him 15 shots before he finally makes it, but there is still a chance. So this gets closer and closer to 0 when you're using geometric, but it never actually reaches 0. There's a really, really small chance that he needs 1,000,000 shots before he finally makes it. All right, last distribution is what is called the Poisson distribution. It's the French word for fish. And here's the difference. And we'll do another example where I'll show you how to distinguish between all three that we've talked about, binomial, geometric, and Poisson, because that's the challenge a lot of times in stats, is knowing when to use what. Here's the difference. In a binomial, you want to know the chance of a specific number of successes. Okay. A different scenario, suppose you want to know the chance that a specific number of things take place within a given amount of time, okay, or area or volume, but usually it's time. So for example, the probability that somebody will take 15 sick days within a single year, that's the type of problem that we use a Poisson for. So here are the conditions, and then we'll do a problem, and then like I say, we'll try to figure out how to use which one in which scenario. Okay, so the Poisson it's still a discrete probability. Okay, it consists of counting the number of times something occurs in a given interval, and it's usually an interval of time, almost always. Okay, or at least the ones that I've seen. I mean, it can be area of volume, like how much in a certain square footage, let's say. Okay, probability is still the same for each case, so that's true of the other ones, and each one is independent. Okay, so the main thing is we want to know how many times something occurs in a given unit of time. Here's the formula, and then I will also show you the calculator way of doing it. So just so you know what these numbers mean, mu, we know what that means. Mu is the average. E is a number on your calculator if you've taken Algebra 2 or pre-calc or calculus. It's the number, it's kind of like pi. It's 2.718. And if you're interested, there's a pretty cool explanation on YouTube of where E comes from. You just search that up. I think I have a video myself, but you could probably find better ones. And then this mu and the exponent is still the same, and x is going to be the number of occurrences, and that exclamation is factorial. So it's a weird formula. There is a proof if you're interested about where that formula comes from. You certainly don't need to know it to do these problems, though. Okay, this is the proof, and you can see the URL is right there. But I don't necessarily have time to explain that proof right now, so let's do the problem. Okay, the mean number of accidents per month. So remember, Poisson is used when something's happening usually in a given amount of time. So the fact that they're telling us that something is happening per month, that's a good sign that we'll be using a Poisson distribution. And I'll show you how to do this both by hand and in the calculator. Okay, so I'm just going to rewrite the formula right here. And that's supposed to be a mu, by the way. Okay, so we need to know three things. We need to know what mu is. We need to know, actually only two things, and what x is. You might say, well, don't we need to know what E is? E is always the same. E is the number on your calculator. You can find it, by the way, if you're curious where it is. It's right above, on mine, it's right above the division key. So if you look right above it, there's an E. So if you hit second division, and then press enter, it should pop up this number, 2.71828. I know it looks like it repeats, but it actually doesn't. It goes on forever. It's a rational number like pi. So that's where you can find E. Okay, what is the probability then in a given month? So the mean number of accidents per month is 3. So mu is 3. What's the chance in a given month 4 accidents will occur? So we're looking for 4 as our successes. Remember, x is the number of successes. And again, we don't mean it's getting in an accident means that you're successful. It just means for this particular experiment, that's what we want. So we just have to plug stuff in here. So mu is going to get plugged in for 3. 3 to the x, so that means 3 to the 4th. E to the negative 3, and then it's going to be over 4 factorial. Okay, if you plug that number into your calculator, you will get the answer. I'm going to show you how to do it it's not really all that much shorter, but here's another way to do it. Go to second vars. This is another way to get the same number. Second vars. Go down to the same place as you used binom and geometric before. This time you want Poisson. Okay, and then you want PDF. Okay, do not use CDF. That's something different. PDF is when you have we want exactly 4. Okay, the CDF type stuff is when you're using things like at least or at most. So Poisson PDF. Okay, you will click on that, and it's going to ask you two things. It's going to ask you this, and that is just another symbol for mu. This is called lambda. It's a Greek letter. Mu and lambda are interchangeable. So for lambda or mu, you would put 3 because that's what it is. And then the x value you would put equal to 4. I'm going to do that off screen right now. Press enter, and I am coming up with a number of 0.168. Okay, and what I'm going to do is put that in my calculator as well, and if you want to verify for yourself that it works, obviously you got to be careful with parentheses here so that that works out. But when I put this number in right here, I do get the same value. 16.8% chance that where there are three accidents on average in a given month, you'd have 4. So, you know, obviously if they say what's the chance that you'd have 15, that's a lot less because the average is only 3. 4 is only slightly higher than average, so still a possible option. Okay, I'll show you one more. There is a way to do these problems with the table again. So we've talked about this before. This is just instructions in the calculator on page 217 in the book, showing you how to do it. Okay, one more thing I want to show you. There is a table. If you want to do it, the table is in the back of the book. It looks like table 3 in Appendix B. You could do the same thing. So it says a population count shows the average number of rabbits per acre. So we said it's usually a time, but this is an example of an area problem. It doesn't have to be per month or per day. It could be like per acre. Okay, average is 3.6. You would go to the table, find 3.6. Find the probability that 7 rabbits are found. So our successes is going to be 7. So we trace over, and it looks like there's a 4.25% chance. So that's how you could use a table, but of course you don't have to. You could use the other way as well.